All right, guys, welcome back. We are continuing our discussion of route optimization. We're actually in our last topic of route optimization, and this topic is going to be fast reroute for Eigrp and LFA for OSPF. That's what we're going to be discussing in this lesson. And then we're going to get into some of our future lessons. We're going to get into things like MPLS. We'll actually spend quite a bit of time, probably a couple weeks on MPLS. And then we're going to just wrap up the course. There'll be a couple of things that we'll be doing. I'll probably be adding a couple of basic topics. And then we're also going to take a look at maybe setting up our capstone meet and greet, if you will, to discuss what to do about the lab, when to do it, and so on. So let's go ahead and continue with our discussion here. We've got a basic topology that we're working with. In this particular case, I had to switch over to a different topology for this lesson because, as we saw from our previous discussion, we need an S-train for this particular feature because this is a service provider function. So in our next section, we're going to take a look at the Eigrp IP fast reroute, the OSPF loop-free alternate feature, which is essentially very similar to what Eigrp's feasibility condition is. Basically, OSPF borrows this concept, if you will, or this procedure to create the same type of logic in order to create a backup path for our primary loop-free path. All right. Now, we want to make sure that we take this particular feature and we are going to, sorry about that, we're going to take this feature and we're going to try to use this feature for fast convergence, basically as a proactive convergence technique. We talked about this in some of our previous lessons, right? The concept of convergence with regard to any of these protocols. There's a few steps involved with convergence. Let me go ahead and pull up that slide here. That's our BFD discussion. And here are the four major factors affecting the convergence time. How long does it take for us to detect the failure? How long does it take for that information to be locally registered and then propagated to the rest of my peers? How long does it take for me to then locally recalculate my database and then update the fib and the hardware tables and so on? So those are some of the concerns that we have. And we talked about, some of the ways that we can handle this. But the idea is that we want to be proactive versus reactive. And a lot of the reactive mechanisms, like doing fast hellos or bidirectional forwarding detection, LSA and SPF spacing, fib prefix prioritization, we talked about all those in some of our previous lessons. Now we're moving into the proactive optimizations. Of course, the standard process in Eigrp would be to make sure that we engineer in some sort of feasible successor. But we're going to talk about how we can even make that process more efficient by using this IP fast reroute option. We're going to talk about the OSPF loop-free alternate routing option, which is essentially a combination of the IP fast reroute along with the concept of the feasibility condition that Eigrp introduces. We're not going to talk in this lesson about BGP prefix independent convergence. We're going to save that a little bit later on. One of the things that is actually missing from this list here is, in fact, the Eigrp IP fast reroute option, and that's IP FRR, which is what we're going to talk about in this particular lesson. So we're looking at now optimizing our routing protocols by introducing these proactive convergence techniques so that we're not having to react to a particular failure. We're going to have the opportunity to do our failure detection, reduce the time for the event propagation and the calculation, and ultimately the installation into the routing table. Now, there are certainly ways that we can do that that are defined as proactive, but there's even more efficient ways, and that's what we're going to be talking about here. We're going to break up this discussion into two different parts. We're going to take a look at the very basics of IP fast reroute and LFA in this discussion. And as I stated in our kind of our introduction, we're going to be taking a look at MPLS. And then once we go through the basics of MPLS, it's going to make a lot more sense why there would be some sort of per prefix priority for particular routes that we would want to install in the topology. And once we understand that, we're then going to come back to LFA and talk about it in more detail and look at the remote LFA feature of OSPF as well. Now, let's just do a quick review, and feel free to ask questions if you have any questions. But let's just do a quick review of, because we're going to start with the Eigrp, a quick review of the feasibility condition within Eigrp. Let me pull up my paint window here. So if I was looking at a basic topology in this particular case, we have, say, for example, R1. And this is all going to be from the perspective of R1. Sorry, that'll be R2. And we'll throw in R3 here. And let's just say we have another path here. Here's R4, R5, and finally R6. And let's say that both of these routers have reachability to network X. Now, when it comes to routing, this is all going to be from the perspective of router 1. When it comes to routing, obviously, from a routing decision standpoint, from a protocol standpoint, we're going to choose our best path solely based on the metric, right? Whether it's cost in OSPF or whether it's the feasible distance in Eigrp, the overall path metric is how we choose which path becomes our successor path. So let's say that this path is the successor. It has a feasible distance of 2,000. And let's say that this bottom path has a feasible distance of 2,500. All right? So that means that the top path becomes the successor path. And the only decision that Eigrp has to make to decide which path is the successor is which one has the lowest overall path cost. Now, this is a distance vector routing protocol, so in essence, router 1 is learning about destination X from its peers. It's not learning about it directly from router 3 or router 6. Rather, it's learning about it through routing by rumor, and router 2 is reporting the distance to network X. That is referred to as the reported distance. And let's say in this case that the reported distance is 1,500 for this top path, and the reported distance for the bottom path is, let's just make it, in this case, 2,000. So in essence, what I'm describing here is this is what R2 is advertising to R1 as the overall metric. So that ends up being router 2's feasible distance to network X. And R4 is advertising to R1 as the metric, which is R4's feasible distance. And this is what becomes the reported distance. Now, the reason this is important to understand is because in order for us to identify a loop-free alternate path in Eigrp, meaning that if the primary path fails, the backup path can be immediately inserted into the routing information base because we've already determined that it meets the feasibility condition. So the feasibility condition states this: if, and we'll say that this would be a feasible successor if the reported distance of the backup path, we'll call this just a little b, has to be less than the feasible distance of the successor path. Okay? Now, this is Eigrp 101. This is not anything that you haven't learned in CCNA or CCNP. It's a basic feasibility condition check. It is a way for Eigrp to identify a loop-free alternate path to the destination that could then be inserted into the routing table immediately if the primary path fails. And in order for that to happen, that backup path cannot be part of the original path. This check verifies that. There's no way that this backup path could be part of the original path if the reported distance of that backup path is less than the feasible distance of the successor path. So in this particular case, we do not meet the feasibility condition because the reported distance of the backup path is not less than the feasible distance of the primary path. So one of the proactive approaches that we can take in ensuring faster convergence and to make sure that we can meet faster convergence requirements is that we can modify metrics along the path on this link here or this link here or even potentially this link here. We can modify metrics on those links so that we do meet the feasibility condition, because we know that this is not a loop per se. Yes, it's an overall loop, but I'm talking about the bottom path is not included in the top path. So we can do some traffic engineering, we can modify some delays or some bandwidths, and that'll provide us the ability to ensure that we have a loop-free alternate path. Now, what does that mean from a convergence standpoint? It means that if the primary path fails, then the backup path can immediately be used and put into the routing information base. But it still has to be installed, okay? Even though we don't have to send a query, we don't have to wait for a query reply, we still need to install the route. And that takes time. That's going to take effort and time. All right? Now, going through all the numbers, all right, we talked about Eigrp and reconvergence. We talked about there's a difference between reconvergence that have paths that have these feasible successors and then ones that do not. And certainly if, as it is right now, this would not meet the feasibility condition, which means that we would have to then send a query. Router 1 would have to send a query to router 4. Router 4 would then have to propagate that query down to its peer, and then router 5 would have to propagate it to its peer, and eventually they would all have to respond with a query reply, a reply packet, and then eventually we can install the route. Okay? So that means that the route, in essence, since we did not have a feasible successor, it's going to send the successor, which is the network X path, into an active state, or send the route into an active state. And again, that means that we need to send a query to my adjacent neighbors and ask them to do, ask them, hey, do you have an alternate path to a particular route? Now, as we talked about in the Eigrp query process, we can bound this query process by changing summarization. For example, if there were a bunch of networks behind this router, maybe 5 or 6 or 7 or 8 or 9 or 1,000 networks, whatever it might be, rather than sending in each of the networks independently, we would send them in as a large summary. And if one of those independent networks went down, it still would not affect our route calculation because we're only calculating the route to the summary. We're not calculating the route to the individual prefixes. So that's one way we can kind of limit this idea of reconvergence. So that we don't have to send a query, we don't have to reinstall routes into the RIB or into the FIB because we're not actually changing the routes. The routes are staying the same. We can also do query scoping if we have stub routing or the ability to do stub routing. In this particular case, stub routing would not really work, but there may be a scenario in which you want to reduce the number of queries that you have to send to peers, and maybe some of those peers are stubs, and you don't want to send a query to those particular stub routers, which then, again, reduces the overall time it takes to reconverge. But in either case, whether it's summarization or Eigrp stub routing, it's not the ideal case. We want to be able to say, my primary path went down, and if I have a pre-calculated path, then I never need to send the route into the active state to begin with. And that pre-calculated path in this case would be what we're defining as a feasible successor, or an OSPF as an LFA, a loop-free alternate path. And that's ultimately what we're talking about in this, excuse me, in this case, is the ability to design that into our topology. But it goes a little bit further than that, and we'll learn about that with the fast reroute and the LFA options later on. All right, so let's say for those that do already have an alternate path and it happens to be loop-free, maybe we change this number here and we make that a, I don't know, maybe an 1800. All right, now we meet this condition because 1800 is less than 2000, so that means we have a loop-free alternate path. And it's just simply a matter of whether or not the metrics calculate to the particular value. That 1800 is really just the feasible distance to network X from router 4. All right, and that's calculated using the standard Eigrp composite metric. So if we already have an alternate path and it's loop-free, we don't have to set the route into an active state. The only thing we need to do is promote it to the successor, install it in the routing table, install it in the forwarding table, and then we can continue to route through that particular path. Now, it sounds like it might be a lot of work, but it doesn't take a whole lot of time. If I've already got this loop-free alternate path calculated, all I simply have to do is, and it's going to be based on the platform, of course, is run the, I don't even have to run the algorithm, I just have to kind of reinsert that route from the routing into the routing information base for Eigrp, and then and the global rib, and then I have to put it into the fib. Now, the disadvantage of doing this is that if Eigrp is already saying the feasible successor is loop-free, and we calculated this based on that feasibility condition check, I still have to go through the process of inserting it into the routing table, into the rib, and then I have to take it from the rib and I have to put it into the software Ceph table or into the forwarding information base, right? Now keep in mind that we have lots of places that we can store routes in a router, and maybe that's perhaps a little bit where it might be confusing. The Eigrp topology table is Eigrp's rib, if you will, Eigrp's routing information base. And then you have your global rib. Your show IP route shows you your global rib, your global routing information base. And then you have your show IP Ceph, which is going to show you your hardware forwarding table or your forwarding information base. So there's lots of places that this information is stored, but it has to be populated. And it can't be populated until it's actually been determined that we can go ahead and use that. So depending on the platform, I may have to write that information down to the line card. I may have to move it from the fib to the TCAM if I'm doing some sort of hardware forwarding. So I'm going from a software forwarding information base to a hardware forwarding information base. But here's the thing. If I already know that that backup path is a loop-free alternate path because it meets the feasibility condition, that is a standard check that Dual does as part of Eigrp. If I already know that you're a loop-free alternate path, why not just pre-download that path before the failure occurs? All right? And that's in essence what the whole logic of fast reroute means. Now, whether we're talking about IP fast reroute in Eigrp, or the loop-free alternate option in OSPF, or BGP pick edge, or we're talking about MPLS traffic engineering with fast reroute, the ultimate goal is always the same in every single case, right? We have a primary path, and we have a backup path, and we have pre-written into hardware so that if I need to change, the only thing I need to do is to move this pointer reference at the ASIC level. We're talking about at the hardware level, the application-specific integrated circuit, and I can continue to forward to the next hop, or I can forward towards a different interface if I need to. All right. Now, in the case of Eigrp, the configuration, as we saw previously before we had to kind of start over, is pretty simple. We go into the Eigrp named process. We go under the topology base, And that's going to be, well, it depends on whether or not you're running address families or not, or multiple address families. But in most cases, it's going to be the default topology base. And we're simply going to say, I actually have a note right here. We're simply going to go in and we're going to say fast reroute per prefix. And then we can specify all, or we can specify it based on a route map. Now, with the route map, we have a choice, right? Keep in mind what we're saying here, right? We're saying, look, Eigrp has all these routes calculated, and we've calculated not only from our successors, but we've calculated all of our feasible successors. And there might be 4 or 5 or 6 different feasible successors, depending on how many routes you have to a destination, or how many different paths you have to different destinations, and so on. And what we're doing in this case is we're saying, look, take all those feasible successors, or take the routes that we reference from the route map, right? It could be based on a route tag. It could be based on specific characteristics of the route itself. We could use a prefix list to reference prefix lengths if we wanted to, and then reference the prefix list from the route map. So the route map gives us the flexibility of identifying which particular routes we want to use for this reroute option, this fast reroute option. We may want to limit it, because there are certainly, in a lot of cases, some routes that are more important than other routes, and we don't want to take up resources inserting or pre-calculating these backup routes for paths that just aren't really that important. We may be limited to a certain amount of resources as well on the platform, which is then going to limit us to which routes that we would or would not want to insert. So Mike has a question here. He says, is there a reason you wouldn't use this? There really isn't, actually. In the past, there may have been, because in the past you maybe had routers that didn't have as much processing power, or they didn't have as much memory. But for the most part, there's really no reason not to implement this particular feature in most of your modern router platforms, because first of all, your routing database is probably not that large. And secondly, your routing platform is probably adequate to be able to do these calculations. It would be platform dependent, but I would say for the most part, most of my ISR routers and most of my routers that I would even be concerned about this on would be powerful enough to be able to handle this. So in essence, yes, you're right. It would be something that you would probably make part of your default configuration, this fast reroute option and the OSPF LFA option. All right. Follow-up question. It basically finds the next best route and makes it the backup. It does more than that, actually, because we're already calculating the next best route as part of the dual process. Eigrp, by default, out of the box, figures out what the successor is and what the feasible successor is. So it does that as part of the standard algorithm process. But in this case, the feasible successor never leaves the topology base, right? Never leaves the actual Eigrp topology table. It's only stored in the topology table, and if the successor fails, then we extract it from the topology table. We put, in essence, promote it to the primary route in the routing information base, and then insert that route into the fib. What this feature does is it takes advantage of that pre-calculated feasible successor, and it does all that stuff in advance. So the route actually shows up, and we'll see this in the configuration, how we can verify whether or not a route was pre-calculated, but the route actually gets removed or extracted from the topology table. It gets put into the global rib and into the fib, not as a route per se, but as a backup route. So that in the event that the primary route fails, all of those insertions have already taken place, reducing the amount of time it takes to switch over to the alternate path. All right. And yeah, and the pointer reference is changed in the TCAM, right? The hardware table, right? Everything is done using these hardware pointer references in the ASICs. And in essence, we're taking the old pointer reference to the old route and pointing it to the new route that's already in the hardware. All right? All right. So that's the idea, right? Why not just pre-download the path before the failure occurs? And in essence, that's what fast reroute is. Now, whether, like I said, we're talking about it in Eigrp or BGP or whatever, the goal is always the same. The backup path gets pre-written into hardware, so that if we need to change, the only thing we do is move that pointer, as Ken said. All right. Now, like I said, we go under the topology base configuration, and we simply execute the command fast-reroute per-prefix. And again, whether you decide to apply this to all the routes in Eigrp or to only a subset of routes, that's up to you. All right. It depends on what your restrictions are on the platform and so on. All right. Now, one of the things I do want to point out, though, is that this feature only works with loop-free alternate paths. So if you have alternate paths that do not meet the feasibility condition, nothing is going to happen with this feature. So you still have to design in to your topology loop-free alternate paths, because without those, nothing's going to happen, right? This only allows us to insert those routes that are already identified as loop-free alternate paths. All right. Now, there are other details beyond this particular configuration, and like I said before, we're going to talk about those after we talk about L3 VPN, because there's actually a reason why you would not want to install all the potential backup paths and say there's only a certain portion of the network that's going to get written down to hardware. Part of it does have to do with the actual TCAM size limitation. So the line card has a memory limitation at the port level. Depending on how many prefixes you have, you may or may not be able to fit them all into the hardware. Mike has another follow-up question here. Let's see. What is the performance gain with Eigrp versus dual and the feasible successor? I'm not sure what the answer to that is. I would say it would greatly depend on what the current load of the platform is, right? If you've only got about 100 routes or 200 routes in your database, and you've already got your feasible successors calculated and the router's not doing a whole lot of work, I don't know that you would see a whole lot of performance gain between, we're talking about milliseconds of difference. And I'm not sure what the exact measurement is, but I've seen convergence scenarios where we just simply rely on a feasible successor, and convergence is rather quick. We might lose one ping or maybe one packet or whatnot. And maybe we can try to demonstrate that here. We only have 4 routers and a couple of routes, so I don't know that you would see too much of a difference, but I would imagine as you scale up and you scale the protocol and you scale the number of routes and the number of peers that I have to communicate with and add all those factors in, that's where you might see a kind of a larger performance gain. All right. On the flip side, you are going to be taking up memory in the TCAM or in the ASICs for stuff that's not being utilized. So if those are already taxed with active information, adding this fast reroute feature may overtax those resources, and you might see a performance degradation. So that would be something to consider as well. All right. All right. The same thing can be said, I suppose, if you decide that maybe there are some routes that are more important than other ones. In a layer 3 MPLS VPN environment, typically the /32 loopbacks are the ones that are going to be part of our tunnel destination endpoints. And like I said, we're going to come back to that after we talk about a couple of topics with the L3 MPLS VPN. because some of the logic is really not going to make sense until we know how those MPLS tunnels work and why we would prefer the /32 routes over any other route when we're going to populate that forwarding information base quickly. All right. Now, I'm not going to pull up the documentation for this, for EIGRP fast reroute and OSPF LFA. You will see if you go out and do a search, it's typically going to be under the IRI category, meaning the IP route independent category. And you might have to do kind of a reverse lookup by using the master command list. But keep in mind that this is and this is what we ran into yesterday, this is a feature that is supported on the S train, not the T train or the M train. The technology train or the main train, it's under the service provider train. So you have to be running a service provider image to be able to support this particular feature. Okay. Typically it's 15.3S or 15.4S, whatever it might be, and so on. All right. It is a service provider feature. You would most likely see documentation related to it for ISIS as well. This is a feature that can be implemented with ISIS as well. All right. So we're not going to look at a sample configuration. I'm just going to kind of go through the process of doing the configuration here. But there are some other things to consider. With OSPF, it's a little bit more complicated. There's some tie-breaking rules, and that has to do with what we call a shared risk link group, or SRLG. That's kind of beyond the scope. I kind of went through this example yesterday. I said, hey, if we have a DWDM strand, a fiber strand, and we're using DWDM, dense wave division multiplexing, so basically fiber optic multiplexing, and we're supporting multiple customers over that strand, and I'm learning about a destination through customer A. If the strand goes down, I'm not necessarily going to want to try to reroute or refine that destination through customer B, because they're basically going through the same physical fiber path, and that would mean that they're part of a shared risk link group. Now, Ken stated here, if this is only supported on the service provider train, why is it in the blueprint? Well, frankly, MPLS, which is heavy in the blueprint, as well as more of a service provider function, right? But these are advanced routing techniques, and this is a routing and switching CCIE. So I don't know that it's going to have a lot of weight on the lab. It's certainly going to be something discussed in the written exam and maybe in the core, the enterprise core exam as we move into the new exam models later on. But in my experience from when I took the labs, we weren't really dealing too much with service provider functions, and fast reroute and LFA were not in my lab. But that doesn't mean it's not something that they don't want you to know about. It's still certainly an important feature as far as proactive convergence techniques go. All right. So we spend some time on it. Like I said, I don't know how much of that time is necessarily useful for the lab, but it's definitely an interesting feature to take a look at, particularly from the OSPF side. On the EIGRP side, it's relatively simple. OSPF side, it's a little bit more complicated. All right. Now, most of the service provider functions are outside of the scope because they are related to what we call service provider core routing. So we're going to, and we will talk about some of that service provider functionality when we get to MPLS, but it's a pretty straightforward configuration. It's basically only one command. And let's go ahead and go to our topology here. Hopefully it's working as it should be. And I'm going to do a show IP route just really quickly. And our focus in this particular case is going to be from router 1's perspective, getting over to this 4.4.4.4 loopback. In fact, let me go ahead and grab a snippet of this. And I had done some of the pre-configurations here, so hopefully those are still applied. But we're really going to just look at this from the perspective of router 1 getting over to this 4.4.4.4 network. All right. So let's first make sure that we have two neighbors, show IP, Eigrp neighbor. If I can get an E in there, there we go. And let's do a show run pipe section Eigrp. All right, router Eigrp CCIE, topology base. We're running it on all of our loopbacks, and we're running it on all the transit links between the routers. And same thing with router 4, show IP, Eigrp topology. Sorry, neighbors first. So we do have two neighbors. The other thing I want to take a look at is, before I even try to implement this feature, is that I want to make sure, I closed my router here, hold on. I want to make sure that we have a loop-free alternate path. Because again, this is not a feature that's going to work unless I have a loop-free alternate path. So show IP Eigrp topology, and we can see that we do have a successor and we have a feasible successor. I've modified a couple of the metrics here to make the path through from router 1 over to router 2, the successor, and the path going down to router 3, the feasible successor. This reported distance is less than the feasible distance of the primary path. So we actually have the topology in place. And I suppose we could, if we wanted to, I could come in here and do a ping to 4.4.4.4. And we'll do a size of 1400 bytes and a repeat of 10,000. Okay. And I can come into router 2 and go into interface Ethernet 01 and shut that interface down. Now that means that I'm losing my primary path, and I should be switching over to the backup path based on the fact that that interface was shut down. And you can see that a couple of things happened here actually. Now this is more of a weakness, if you will, of we would have to kind of enable BFD to make this not happen, but a weakness of GNS3 in that when you shut down an Ethernet interface, the opposite side of the link still thinks that the Ethernet interface is active. Let me do this instead. I may have to do it this way. Let me let's do enable secret Cisco line VTY 04 login password Cisco. All right, and let me do a no shut on this interface, and then I'm going to telnet to 1.1.1.1. And the reason I'm doing this is because I don't want to rely on the dead peer detection feature, the dead timer in Eigrp, to see the switch over from the primary route to the backup route. So we'll go ahead and do our ping again. And now if I do a show IP interface brief, if I shut down this link, we'll see how quickly we converge. So config T interface Ethernet, and we'll shut down that interface. It should certainly happen a lot faster, right? So we basically lost one packet because the last packet was when I killed the ping. So in that convergence time, we lost a single packet. Now, I don't know by enabling fast reroute if we would not lose any packets. I guess we'll find out. But again, we're dealing with a very small network, a small number of prefixes, so it's not something necessarily that we're going to, we may not see a difference, in other words. All right, so let me do a no shut on that interface again. The adjacency should come up. All right. And we're going to go ahead and implement our fast reroute feature. Now I could, like I said, I could implement this using a route map, and I could say, yeah, let's go ahead and do it only based on this particular prefix, or a prefix with this particular characteristics, a prefix length, or whatever it might be. But we're just going to enable it for all routes in this particular case, just to demonstrate the concept. All right. Like I said, before you do that, you would always want to go and take a look at the topology. Make sure you have a loop-free alternate already calculated, because without the loop-free alternate, this feature doesn't do anything. All right. Now, LFA, or IP FRR, if you want to call it that, is different than ECMP. ECMP allows you to write multiple equal paths into the rib and into the fib by doing routing over those paths at the same time. LFA is not meant to be for unequal cost load balancing, right? It's only for active standby routing. So whether we're talking about it in Eigrp or OSPF or BGP or MPLS, it's not going to be equally load balancing. It's going to say, hey, the primary path is A, the backup path is B, which also happens to be a loop-free path, because we've already calculated that. We're going to write that into the hardware. All right. So I've already kind of pre-configured the topology to meet the conditions that we have to meet in order for us to have that loop-free alternate path. Oops, what happened there? Sorry guys, hold on one second. Let's kill that. Somehow I opened that. All right. So yes, Ken, you're correct. This is failover versus load balancing. And in our particular case, it is proactive failover as opposed to reactive failover. All right. So we know we have a feasible successor. But if we go to the actual routing table and I do a show IP route, show IP route for 4.4.4.4, we can see that we're only using one path, and it's through 12.2. This is the overall path metric. Remember, we're using wide metrics in this case because we're using named mode configuration as opposed to classic mode configuration. All right. So now we're just going to go into our process, show run section Eigrp, and we're going to go config T, and we're going to go into the address family under the topology base, and we're going to say fast reroute. Yay. Fast reroute per prefix. And again, we really only have two choices. Enable it for all the paths in the topology, or enable it based on a referenced route map. By the way, if you do a fast reroute, you can see that there are some other options here. But again, those are kind of outside the scope of what we're doing in this particular case. So I'm just simply going to do a fast reroute per prefix all. All right. Does this require named mode, or will it work in classic mode? That's a good question. Let's see here. We can certainly do that. Let's go router Eigrp 100. So this would be a classic mode configuration, and see if we have an option for fast reroute. It doesn't look like we do. So this looks like it is a named mode configuration, because this is not an interface-based configuration. It should show up if it was an option under this configuration. Let me see if IPv4 unicast, and see if it's under a VRF option. Yeah, well, we'd have to configure a bunch of other things. I don't think it's available in classic mode. I don't believe it is, and that's why we're doing this in named mode. But I'd have to go back and check that. I've always configured this as a feature in named mode, or address family mode, if you will. All right. It's done on the topology base. We want fast rerouting. Like I said, we just basically did it for all the prefixes. Now, if we go look at the Eigrp topology and we say show IP Eigrp topology for 4.4.4.4/32, we can actually see two different entries here, right? And we see that the state of the route is passive. So that tells us that the route is not in the process of being converged. So it should be installed in the routing table. There's only one successor. The feasible distance of that successor is 196689920. And then the backup route, if you will, is 203.971.697. But it does meet the feasibility condition again because the reported distance of this path is less than the feasible distance of the primary path. All right. So far, I don't really see anything in here that indicates that this fast reroute option is enabled. All I can see is that I see my successor and my feasible successor. Now, if we look at the show IP route for a particular prefix, there will be a change here. So let's say show IP route 4.4.4.4. We can see now that we have a listing here called the repair path, which indicates that the fast reroute option has been enabled for this particular path. The repair path is identified as router 3, which is that feasible successor. All right. Now, the repair path is nothing more than the feasible successor. The feasible successor was already in the topology, right? That didn't change. The feasible successor was already in the Eigrp topology. But now the only thing is that this loop-free alternate path is we're going to say that this feasible successor now gets pre-written into the rib, and then we get it written into the fib. So if we were to actually look at the Ceph table and say, let's do a show IP Ceph for 4.4.4.4, we can actually see that the next hop is written. But so again, this is what's written to the rib, the global rib. This is what's written to the fib, the forwarding information base. So in both cases, we're actually identifying an alternate path to that particular destination. So again, what does this save us? It saves us the amount of time it would take to download the route from the Eigrp topology table into the actual line card hardware. Now, depending on the platform that we're using, it could be a considerable delay. It's not something that normally is going to take too long, maybe a couple of milliseconds to do. But generally, when it comes to distributed platforms, the line cards are relatively slow. And in order to write those changes into hardware, it could take some more time. So the idea is that we've already done this pre-calculation. Everything is fine. So we make the changes in the background while we're forwarding traffic normally. And then eventually, if you need to use the backup path, it's already available. So let's do our test again. Like I said, I don't know if it's going to result in only 0 lost packets or not. But let's give it a shot, all right? So I'm going to go ahead and do my ping again. And we're going to go ahead and shut down the interface again. And let's see what happens here. All right. So it looks like it really didn't change much in our case, right? We still lost 1 packet. It says we lost 2 packets here, but we actually only lost 1 packet. Somewhere in here, there's a lost packet somewhere. Who knows where? But we definitely lost 2 packets. Of course, the last one is the one that we would have lost anyway when I broke the ping sequence. So this really isn't a measure of whether or not this feature is useful or not. You really have to look at it in a loaded condition when you have lots and lots of more complex topology, if you will. So, and this is what I was saying before when Mike asked the question, is this something that is going to really save you a whole lot of time? In our particular case, no, because of our topology. All right? But, and yes, Ken, you're correct. That would be very platform specific. Absolutely. The number of lost packets, the amount of time it takes to actually load routes from the topology table from Eigrp into the routing information base and then into the forwarding information base would definitely be platform specific. All right. But we know, based on the show IPsef, we know that it is getting written into the fib proactively because we see the repair reference there. All right. Ken says here, so probably, not sure what you're saying, Ken. Some loss on something like an, oh, no loss on something like an ASR. Yeah, possibly, right? I mean, we see the same kind of results if we're doing things like BFD, but again, BFD is a way for us to more quickly identify the loss of a neighbor or the loss of a peer, but it doesn't really assist in pre-writing the information to the hardware. And that's what this particular feature does. All right? It's already written into the CEF table, so as soon as the primary route goes away, that repair path gets promoted simply by basically moving a pointer in the hardware to say it should be used instead of A, now we're going to use B, and we're going to go ahead and forward the packets out to that particular destination. But again, the logic of this has to do with the feasibility condition. That if, for some reason, if there is no feasible successor, like I said, fast rerouting is not going to do anything for you. It's just going to say, hey, we already have an alternate path. It's already defined as a loop-free path. So we just save us a little extra step later on, pre-download that information from the topology into the fib through the rib. All right? Now, if we go ahead and turn on BFD between the routers with the primary path, we want to make sure we're running fast reroute in both directions. We don't have to necessarily do this config. I can ask the question, why not bypass BFD in favor of LFA? Well, there's a couple reasons, because BFD works in conjunction with, works with adjacencies, right? And keep in mind what the purpose of BFD is. Had I shut down, in this particular case, had I shut down the Ethernet interface on router 2, okay? And there was, say, for example, a switch in between the two routers. Let's go to the diagram here. If I had some sort of switch in between these two routers, let me switch to my custom pin. So I had some sort of switch in between these two routers, and this router went away, or that link went away. We're not going to, LFA is not going to come into play because router 1 is not aware that router 2 is down or doesn't exist anymore. Okay? So in that particular case, even though LFA is enabled and we've inserted the route into the hardware, until I've identified that the peer no longer exists, I can't make that change. So if I use this feature in combination with BFD, that's the best of both worlds, right? Because now not only am I going to be able to identify that the peer doesn't exist, I would also be able to use LFA to do the fast reroute. Okay? All right? All right. Now, I could go through, I suppose, and configure BFD. We've done our BFD lesson. I kind of refer you guys back to that. The only difference with BFD, like I said, is it's going to allow us to detect that the neighbor is down or the peer is down much faster. But we don't necessarily need that. I suppose we could go ahead and configure it under the interface. But I kind of bypassed that process. because I shut down the local interface. And the router's smart enough to say, hey, if my local interface to the peer goes down, then the neighbor is no longer available. All right, but you guys understand what the addition of BFD would do in this case. So BFD would allow me to identify the neighbor's state change quickly in milliseconds, 50 milliseconds or so. And then based on that state change, then I can start using that fast reroute route. Okay. All right. So I'm not going to configure that in this case. We're already at 55 minutes. So I'm going to continue on because we still have to talk about OSPF as well. Just remember, in the case where the routers are running, especially in our case, right? The routers are running in software. So the fib is not actually pre-written into hardware. But in general, it's going to be much faster even in software than it would be to do kind of a normal reconvergence, if you will. All right. So from a configuration standpoint, like I said, very simple. It's only one command. But the whole point is that the network has to be properly engineered in order for us to have a primary and a secondary path. And that secondary path has to be a loop-free alternate path. That's very, very important. All right. All right. If I were to shut that down, by the way, it's one thing I did not show you, is let's go ahead and shut down that interface again. So now we're on our backup path. So now if I do a show IP route or show IP Ceph for 4.4.4.4, it just looks like a normal route in this case. Because we haven't, if I did have another feasible successor, it would continue to install the backup path as long as a feasible successor exists. But in this case, there is no feasible successor because we're down to our last path, which means in essence that there's no backup path. Just looks kind of like a normal route in this particular case. Do a no shut, it'll come back. Okay. Now, in the case of OSPF, the goal is ultimately the same, right? We want to have a primary path, right, that we're using for normal routing. And then we want to have a backup path that we're going to pre-calculate, all right? Now, Eigrp is great for this because it already has a feasibility condition check built into it. So it can already do the backup routing. OSPF is a little bit more difficult because the SPF algorithm is only designed to choose one leg of the tree for regular routing, potentially multiple links of the trees if they were doing something like ECMP or equal cost routing. But normally OSPF doesn't support unequal cost routing, and it simply discards any other path that is not considered to be a candidate in the tree when we actually look at the SPF algorithm. Now the solution for this in OSPF actually turns out to be pretty straightforward as well. Again, based on everything that we've talked about so far, the ultimate goal is that we're trying to pre-calculate a backup path like Eigrp is doing. In OSPF, though, every router is the root of its own shortest path tree. That's the way the SPF algorithm works. Every router kind of puts itself as the root and calculates the best path to each of the leaves in the tree and the branches and so on. So let's say I'm in area 0 and I'm looking at what is my shortest path to all the other nodes in area 0. I know the entire topology because we did LSA flooding. Everyone exchanged their LSAs, and I know how all of the routers are interconnected. I run my SPF algorithm from my perspective. I become the root of the tree, and then I solve the shortest path to every single node. However, at the same time, I have the same input to SPF as everybody else does because we all agreed on the topology, particularly within the area itself, because we have an exact same copy of the database. Sorry about that. All right, so to choose a loop-free alternate path, the logic is pretty simple. I'm going to run the SPF algorithm from your perspective. So I run it from mine first to figure out what my primary path is, and then I run it from other routers' perspectives, and I figure out do they have an alternate path, right? Because that's what we're looking at. Do they have an alternate path, but it has to be a loop-free route in the tree that don't have my protected links in that particular forwarding path. In other words, it has to be a unique path. Now, in OSPF, this is a little bit more complicated, especially when we start to scale it, because now you're not only running SPF for yourself, you're running SPF for other routers, and depending on how big the area gets, remember this is going to be something that's limited within the area because we have to have a common database. This could be one of the scaling issues or the scaling factors of doing LFA and OSPF. We'll actually see this later on in MPLS. There's a reason why you would want to limit what the particular prefixes are that you want to use. And like I said, generally it's going to be just those loopbacks, which are the endpoints of our MPLS tunnel. Overall, though, the logic is basically the same. Configuration is not complex. It's just because we don't have that feasible successor option in OSPF, it's a little bit more limited. All right, I have a primary path. I want to calculate a backup path. And to do this, I'm just going to run SPF again. The configuration is exactly the same as it is in Eigrp, but we need to go ahead and enable OSPF. So the first thing I'm going to do is I'm going to kill Eigrp. So config T, no router Eigrp CCIE. All right. And I'm just going to do a router OSPF 100. All right. And I'm just going to be lazy here. I'm just going to say network 1.0.0.0. And let's do a block of 4. Let's do a block of 8. So 7.255.255.255 area 0. That'll take all of the loopbacks. I should just start this at 0. That'll take all the loopbacks and put them into, should take all the loopbacks and put them into area 0. Let's just do it this way. Network 1.0.0.0. 0.255.255.255 area 0. And network 2.0.0.0. 0.255.255.255 area 0, and network 3.0.0.0, 0.255.255.255 area 0, and finally network 4.0.0.0, 0.255.255.255 area 0, and then finally network, try to use my tab completion there, 172.16. So all I'm doing is setting up OSPF, and I'm placing all of the interfaces into area 0. All right, so I should get some adjacencies popping up here for OSPF. If I do a show IP protocols, I should see I'm only running OSPF, show IP OSPF neighbor. We're still converging. All right, we're in the wait state right now because we're converging over a multi-access network, but it'll come up in a second here. All right, so like I said, the configuration is, well, I said it's exactly the same as Eigrp. It's not quite the same, but we are going to use the fast reroute per prefix option. Now, again, there are other options here, and we'll talk about it in more detail later when we're talking about layer 3 MPLS VPN. So let's go config T. We're just going to enable it actually on router 1 here. Router OSPF 100, fast reroute. And you can see here we do have a couple of options, keep all paths or per prefix. And then we have the option, excuse me, of enabling it, doing tie breaks, or doing a remote LFA, setting the remote LFA parameters. We're just going to enable it, which is basically the same as saying all. Let's do area 0, and we'll do prefix priority. We could have just done, let's do high in this case. High would be the loopbacks. We'll talk about this again, like I said, when we get into I'll go through it, the option of low and high in a little bit. But in this case, high would automatically include, as part of the documentation, it would automatically include the loopback interfaces, which are our /32 interfaces. All right. Now I've only enabled it per area 0, but in this case, that's fine. That's the only area that we're running. All right. The LFA calculation is a little bit more complicated as well when we get into doing multi-access nodes with DR and BDR elections. So the other thing that I want to do really quickly is I want to set all of my interface types 01 IP OSPF network point to point, and let's do that for number 2 as well. All right. Show IP OSPF neighbor. So we should be point to point show IP OSPF. I should have 2 neighbors here. Is that interface still shut down? Let me see if that interface is shut down. Show IP interface brief. Interface is up. Show run. Make sure it took the config here. Point to point, point to point. Okay, that's good. Router. Oh, I see. Let's get rid of that. Show IP interface brief. Show run. Yeah, let's fix that. I don't think router 2 got any of its configs because it was stuck on when we were messing around with router 1 before. So let's go ahead and put those in. IP OSPF network point to point. And router OSPF 100 network 2.0.0.0 0.255.255.255. Area 0 and network 172.16 0.0.255.255 area 0. We were connected to router 1 previously. It's still trying to resume that connection. Clear session. Clear line. And let's see. Let's see if it should connect now, actually, because we're going to want to do the same test. Yeah, there we go. Now it's connected. All right. So let's exit there. Okay. So now we should have our adjacencies. Router 4 should have a couple of adjacencies. Show IP OSPF neighbor. And router 1 should have a couple of adjacencies. Show IP OSPF neighbor. Now again, the only thing I've done at this point is I've enabled fast reroute per prefix in area 0 for the high priority prefixes, which again are the prefixes that are identified as loopbacks. Ken had a question here, why change the network type? All right. I set all the links as network type point to point because when we have a pseudo node or when we have a DR, it makes the LFA calculation a little bit more complicated for OSPF because it has to run the OSPF calculation from the perspective of the DR. So I'm just kind of eliminating that need. In a real environment, you would probably not want to do that. But I'm just trying to make our discussion a little bit simpler in this case, just so we don't have to look at it from the perspective of the DR. Okay? So if I do a show IP route, I should see router 4, we have a path. If I do a show IP OSPF database, I can see that I'm learning about the 4.4.4.4 network. Now I'm not running ECMP in this case because, excuse me. Sorry about that. because if you look at the interface, I did modify the bandwidth on the interface. I think it was on router 1 actually. Show run. From router 1's perspective, I've modified the bandwidth on this interface to make it a little bit less preferred. That was a carryover from our Eigrp configuration, which is what we still want to do anyway, because we don't want ECMP enabled in this particular case. And by changing the bandwidth, we've in essence changed the cost of that particular link. If I hadn't had that bandwidth, it would have been equal cost. But LFA is different than ECMP. If we have ECMP, that's fine. I mean, you're going to be forwarding in both directions, but if one of the paths fail, then you're simply going to use the other path. And because you're already forwarding in multiple paths anyway. LFA is when we're trying to do active standby, like I said. So we want the primary route and we want a backup route, and we did that already. All right. In the case of BFD, again, we could use OSPF to utilize BFD, but you know, we could set up the BFD properties on the interface. I'm going to basically use the same approach to failing over the network. And it's going to end up being the same result, right? We're going to see maybe one lost ping or something like that. The idea of having BFD, again, is to quickly detect the failure. Without BFD, we would not be able to quickly detect the failure of the neighbor, which defeats the whole purpose of running LFA to begin with. All right? So we have to take all the variables into account in the failover process. Failure detection, the event propagation, the recalculation, the fib update, all those things. Okay? In fact, let me do a show run pipe section router. Show run pipe section router, because I want to grab this command here and put that into my notes. The notes are a little bit anemic for this discussion because, well, there's really only one command to enable this feature for what we're trying to do. All right? So we would set up BFD. If BFD goes down, it's going to tell OSPF. We should be able to restart the calculation and so on, and whatnot. All right? Now, if I was to look at the documentation for fast reroute, it gets a little bit confusing because, as you can see, the syntax is significantly different than Eigrp. But in this case, I don't really want to get into the weeds of high priority prefixes and low priority prefixes. In essence, based on the documentation, and if you were to go to look at the S-Train documentation, you go look at a configuration example, you'll see fast reroute per prefix. There is a difference here. Obviously, with OSPF, they categorize the prefixes as high priority versus low priority. The high priority prefixes are going to be your loopbacks. That's defined in the documentation. It's defined in the implementation. Now, in this case, we're actually trying to protect the loopback, so it doesn't matter. We can just say, let's do a fast reroute per prefix enable, and then we should match the loopback, and we're trying to use. But you can see there's some, if you go to the documentation, you can see that they do have some other examples. You could say, for example, match route tags, maybe matching a tag of 888 or whatever, and then anything that matches tag 888 would have fast reroute applied to it. So you do have options of limiting which prefixes are going to be included in the fast reroute feature. All right. So in our case, we just did fast reroute per prefix enable. We didn't necessarily have to specify the area. In fact, I'll go ahead and take that out. So if this was a router that was participating in multiple areas, it would be enabled now in multiple areas as opposed to only in area 0. That's another thing to consider as well, is if you want this to run only in one area. Because keep in mind now, with OSPF, it's a little bit more process intensive because the router is now having to calculate not only its own SPF tree, but it has to look for those loop-free alternate paths by running the SPF algorithm from the perspective of all the other peers in that area. So this may be something that you limit to one area for that reason. All right. So we have this configured. Now let's take a look at our backup paths. We would do that, by the way, by just doing a show IP route repair paths. All right. So let's go to router 1, show IP route repair paths. And this is, in essence, our, these are not our primary paths. These are our backup paths, right? If we look at 4444 specifically, let's see here. Let me do a show IP CEF 4444. Well, it is going to 12.2. Why is this showing 12.2? We should be seeing our repair paths. Let me check something really quick here. Let me see if I am getting information about 4.4.4.4. So 5 links. I should be getting this show IP OSPF database router. I should be getting this from router 2 and router, let me look at the topology. Should be getting this from router 3 and router 2. Actually, all routers for the 4444 network. I see one. Of course, I'm not going to originate it. I am the router. But I should be getting it from router 2, which I am, point to point. And I should be getting it from router 3, which I am. And I should be getting it from router 4, which I am. Router 4. So I'm definitely learning about the prefix from each of the routers. Not sure what's going on, but we should definitely see this as a protected path. If I do a show run pipe section router, we have low. Let me change this to high. Oops. Let's see, router. Show IP route, repair paths. Yeah, it should be reporting here for the repair paths. It should be reporting that 13.3 is a repair path, and 12.2 is the primary path. But this is the thing that's a little bit concerning, is we're not seeing any paths protected. Let me try one more thing. Show run interface loopback 0. Yeah, see, that's enabled by default. Because I went into the interface, and one of the things I did was I turned on fast reroute per prefix protection on that interface. But that's enabled by default. So I'm not sure what's happening here with GNS3, but we should be definitely seeing 13.3 as a repair path. And we should also see a pointer in the CEF table for, just like we did with the Eigrp. I'll probably take a look at this. I'll leave this running and maybe play around with it a little bit more, and maybe add a little bit to this video if I need to. But let's wrap it up. Ultimately, we should be able to look at the regular routing table and then look at the difference in the output for the show IP route repair paths, and that would show us what the primary path and the backup path is. But the end result is the same in this particular case. When we look at the routing table for a route, it says we have our primary path, but we also have a loop-free alternate path, or LFA. We're not seeing that for some reason here. I don't know if it's a code issue or a GNS3 issue, because I know that the configuration is accurate. So, and we've done this in both directions. All right. So if a failure occurs, we still have to do the flooding. All right. So we still have a regular update procedure. That's going to happen, where I go ahead and tell all my neighbors, now this link is gone, you need to recalculate your SPF. For FRR for Eigrp and OSPF, these are proactive convergence mechanisms, because we're saying, hey, when a failure occurs, continue to forward. It might not be the best optimal path total, but in the meantime, while you're recalculating, I don't want to drop any packets. And that's ultimately the idea. I'm a little disappointed that we didn't see it working in OSPF here, but again, I'm going to play around with this for a little bit and see if I can't figure that out. If I can find out what the issue is, I'll just add the solution to the end of the video here. All right, so we'll wrap it up for tonight. We are going to continue this week with MPLS, start with our introduction, and then we'll get into the weeds with MPLS. So we'll see you guys in the next lesson.